Welcome, my friend, as you settle into this quiet moment, letting the day's concerns soften and recede. Tonight, let us gently explore a concept that cradles all existence, that holds the stars and the dust, the near and the far, in its silent embrace. Let us talk about space. Imagine, if you will, the very fabric of everything. Space. It is often described as a three-dimensional continuum, a canvas stretching endlessly, providing positions and directions for all that is. Picture yourself floating in a calm, dark ocean, where every point you can perceive around you, above, below, to the sides, forward, backward, defines a position. This boundless expanse, this silent volume, is what we intuitively understand as space. For centuries, this understanding remained largely within the realm of what we now call classical physics. Here, space was often conceived in those three familiar linear dimensions: length, width, and height. Simple, intuitive, tangible. But as our understanding of the universe deepened, as minds pushed beyond the immediate, this seemingly simple concept began to unfurl into something far more profound, far more intricate. Modern physicists, with their instruments and their equations, have invited us to consider space not in isolation, but in a delicate, interwoven dance with time. They speak of a boundless four-dimensional continuum known as space-time. Close your eyes for a moment, and let that idea gently swirl in your mind. Space-time. It suggests that time is not merely a separate river flowing through a static landscape of space, but rather an inseparable dimension of that very landscape itself. It means that every event, every breath you take, every thought you form, occupies not just a point in space, but a point in space-time. This deep integration of time with space is a cornerstone of our contemporary understanding of the universe, a realization that has reshaped our scientific cosmology. The concept of space, in all its iterations, is considered to be of fundamental importance to an understanding of the physical universe. How can we truly comprehend the cosmos, the galaxies, the planets, the very atoms, without first grappling with the container they inhabit? Yet, despite its apparent omnipresence, disagreement continues, even among the most brilliant minds, over its fundamental nature. Is space, itself, a tangible entity, a thing that exists independently? Or is it merely a relationship between entities, an emergent property of the way objects interact and are positioned relative to one another? Or, perhaps, is it part of an even deeper, more fundamental conceptual framework, a structure of the mind through which we organize our perceptions of reality? These are not questions with easy answers, and the very act of pondering them is a journey into the deepest philosophical waters. Take a gentle breath, and let your mind drift back a few centuries, to the 19th and 20th centuries. This was a time when mathematicians, with their abstract insights, began to examine geometries that were non-Euclidean. For millennia, Euclidean geometry, with its flat planes, straight lines, and familiar angles, had been the unchallenged king. It was the geometry of our everyday world, of architects and carpenters. But these new geometries proposed something radically different, space conceived as curved, rather than flat. Imagine the surface of a globe, a vast sphere. If you draw a straight line on a globe, it's actually an arc, a great circle. The angles of a triangle drawn on a sphere don't quite add up to 180 degrees. This is a simple analogy for curved space. Now, elevate this idea to 3 dimensions, and you begin to glimpse the profound shift in thinking. This seemingly abstract mathematical concept found its stunning physical manifestation in Albert Einstein's theory of general relativity. Einstein proposed that space itself, or more accurately, space-time, around massive gravitational fields, such as those cr. Aided by planets and stars, deviates from Euclidean space. It literally curves. The presence of mass and energy warps the fabric of spacetime, and this warping is what we experience as gravity. It's as if a bowling ball placed on a stretched rubber sheet causes the sheet to dip, and marbles rolling nearby are drawn into that dip. Experimental tests of general relativity have, time and again, confirmed this incredible notion, demonstrating that non-Euclidean geometries provide a far better model for the actual shape and behavior of space in our universe. Isn't that a wondrous thought? That the very space you inhabit, the air you breathe, the ground beneath you, is not a rigid, flat stage, but a dynamic, subtly curved canvas, responsive to the cosmic ballet of mass and energy? Let's delve deeper into these profound philosophical questions about space, for debates concerning its nature, its very essence, and its mode of existence have echoed through the corridors of human thought since antiquity. Picture the ancient Greeks, their minds alight with curiosity. We find these musings in treatises like the Timaeus of Plato, where he grappled with the concept of the receptacle or chora, a kind of primordial space that existed before forms were impressed upon it. Or think of Socrates, pondering what the Greeks called chora, a term that evokes a sense of interval, distance, or even an empty place. And then there was Aristotle, whose Physics, specifically Book 4, Delta, offered a definition of topos, or place. For Aristotle, place was not an empty container, but rather the inner boundary of the containing body, the immediate environment that encloses an object. This was a very relational view, deeply intertwined with the physical world. Centuries later, the 11th century Arab polymath Alhazen, a genius of optics and mathematics, offered his own insights in his discourse on place, called Fi al-Makan. He introduced a more geometrical conception of place as space qua extension. Here, we see a gradual shift towards understanding space as something with measurable dimensions, an abstract extension, moving closer to our modern understanding. Many of these classical philosophical questions, these timeless inquiries, were reignited and reformulated during the vibrant intellectual period of the Renaissance, and then dramatically recast in the 17th century, particularly with the early development of classical mechanics. This era was a crucible of new ideas, where the very foundations of how we understood the physical world were being laid. And at the heart of this intellectual ferment stood two colossal figures, each with a radically different vision of space. On one side we have Sir Isaac Newton. Newton viewed space as absolute. Imagine an invisible, unchanging, infinite stage, a cosmic arena that exists permanently and independently of whether there was any matter in it. It was, for Newton, an unmoving, eternal backdrop against which all events unfolded, a divine sensorium, a frame of reference that was always there, always the same, waiting for the universe to play out its drama. This absolute space was not affected by objects or forces, it simply was. It provided the ultimate, unchanging coordinates for everything. This concept of absolute space was crucial for his laws of motion and universal gravitation to work, allowing him to define absolute motion and absolute rest. It gave his universe a stable, objective reality. In stark contrast, other natural philosophers, most notably Gottfried Leibniz, offered a profoundly different perspective. Leibniz thought that space was not an independent entity at all, but was in fact a collection of relations between objects, given by their distance and direction from one another. For Leibniz, if you were to remove all objects from the universe, space itself would cease to exist. There would be no relations, and thus no space. Imagine a constellation of stars. The space of that constel. Lat ion is defined by the distances and angles between the stars. If you remove the stars, the constellation's space vanishes. Leibniz argued that to conceive of an empty space, a space without any objects or relations, was a philosophical impossibility, a mere abstraction without any real counterpart. For him, space emerged from the ordering of things, rather than being a pre-existing container. This relational view of space was deeply intertwined with his philosophy of monads and his principle of sufficient reason, where everything that exists must have a reason for existing. The idea of an absolute space, independent of matter, struck him as a violation of this principle, a senseless fiction. Take a moment to let these two contrasting visions gently rest in your mind. Newton's absolute, pre-existing container. Leibniz's emergent, relational framework. Both brilliant, both striving to make sense of the same vast reality, yet arriving at such distinct conclusions. In the 18th century, another influential philosopher and theologian, George Berkeley, contributed to this rich tapestry of thought. He attempted to refute the visibility of spatial depth in his essay Towards a New Theory of Vision. Berkeley, known for his idealism, argued that our perception of depth, our understanding of distance, is not directly perceived by the eye, but is rather an inference we make based on our experiences of touch and movement. It's a learned association, not an innate sensory input. This challenged the notion that space, in its full three-dimensional glory, was something we directly experienced through sight alone. And then, later in the same century, the towering figure of the metaphysician Immanuel Kant entered the debate, offering a synthesis that profoundly shifted the philosophical landscape. Kant proposed that the concepts of space and time are not empirical ones, not derived from our experiences of the outside world, as the empiricists believed. Instead, they are elements of an already given systematic framework that humans possess. They are, he argued, the very structure of our minds, the lenses through which we filter and organize all our sensory input. Kant referred to the experience of space, in his critique of pure reason, as being a subjective, pure a priori form of intuition. What does this mean, a priori? It means prior to experience. So, for Kant, space isn't something out there in the world that we discover, it's something in here, in our minds, a fundamental way we are wired to perceive and understand reality. We cannot experience anything without experiencing it in space and time. It's like the inherent grid of a spreadsheet program. You can't enter data without placing it in a cell defined by rows and columns. Similarly, for Kant, you cannot have an experience without placing it within the intuitive framework of space. This doesn't make space unreal, but it suggests its reality is deeply tied to our consciousness, to the very act of perception itself. It is a profound and revolutionary idea, suggesting that our understanding of space is not just about the universe outside us, but also intimately about the structure of our own minds. Let's now gently shift our focus from these grand philosophical debates to the foundations of the scientific revolution, a period of breathtaking intellectual upheaval that irrevocably changed our understanding of the cosmos. This revolution, understood to have culminated with the publication of Newton's monumental Principia Mathematica in 1687, built upon the insights of several key thinkers who dared to challenge millennia of established wisdom. Newton's theories about space and time, particularly his concept of absolute space, were instrumental in allowing him to explain the movement of objects, from the falling apple to the orbiting moon. While his theory of space is considered the most influential in physics for centuries, it elegantly emerged from the foundational ideas about space laid down by his predecessors. One of the pioneers of modern science, Galileo Galilei, initiated a crucial revision of the established Aristotelian and Ptolemaic ideas about a geocentric cosmos, the belief that the Earth stood motionless at the center of the universe. With his telescope, Galileo observed the moons of Jupiter, the phases of Venus, and the imperfections of the lunar surface, providing compelling evidence that backed the Copernican theory, that the universe was heliocentric, with a stationary sun at the center and the planets, including our own Earth, revolving around it. This was a truly radical idea. If the Earth moved, the deeply ingrained Aristotelian belief that its natural tendency was to remain at rest was fundamentally called into question. Galileo, with his keen experimental insights, wanted to prove instead that motion was as natural to an object as the state of rest. He argued that celestial bodies, including the Earth, were naturally inclined to move in circles, a perfect geometric form. This view elegantly displaced another cherished Aristotelian idea, that all objects gravitated towards their designated natural place of belonging. Instead, Galileo's universe was one of continuous, natural motion, a universe where the laws of physics applied equally to the heavens and to the earth, paving the way for a unified understanding of the cosmos. Following Galileo, another titan of the scientific revolution, René Descartes, sought to completely replace the Aristotelian worldview with a comprehensive theory about space and motion determined by natural, mechanical laws. Descartes sought a metaphysical foundation, a purely mechanical explanation for his theories about matter and motion, free from the mystical and teleological explanations of the past. Cartesian space, as he conceived it, was Euclidean in structure. Picture it, infinite, uniform, and flat. It was, crucially, defined as that which contained matter. And conversely, matter, by definition, had a spatial extension. This led to one of Descartes' most famous and significant claims: there was no such thing as empty space. The universe, for Descartes, was a plenum, a vast, continuous expanse filled with an infinitely divisible, subtle matter, moving in vortices. If you could perceive a space, it had to contain matter. A true vacuum, an absence of matter, was an impossibility within his system. This stands in stark contrast to later ideas, like Newton's absolute empty space. The Cartesian notion of space is closely linked to his broader theories about the nature of the body, mind, and matter. Descartes is famously known for his declaration, "Cogito ergo sum, I think, therefore I am." This assertion posits that the only thing we can be truly certain of is the fact that we can doubt, and therefore, we can think, and therefore, we exist. His theories belong firmly to the rationalist tradition, which attributes knowledge about the world primarily to our ability to think, to reason, rather than solely to our sensory experiences, as the empiricists believed. He posited a clear distinction between the body and the mind, a profound separation referred to as Cartesian dualism. For Descartes, the material world, including space and matter, operated purely mechanically, while the mind was a distinct, non-physical entity. This division profoundly influenced subsequent philosophical and scientific thought, shaping how we understood the relationship between the physical universe and our conscious experience within it. As we gently drift through these profound ideas, notice how each thinker, each philosophical current, adds another layer to our understanding of space. From the ancient contemplation of Cora to the geometric extensions of Alhazen, from Newton's absolute stage to Leibniz's relational dance, and Kant's a priori intuition, and finally to the scientific reimaginings of Galileo and Descartes, each offers a unique lens through which to view this fundamental aspect of reality. Consider the implications of each perspective for a moment. If space is absolute, as Newton believed, then there is an underlying, unchanging reality, a cosmic grid that exists whether we observe it or not. This perspective lends itself to a sense of cosmic order, a deterministic universe where all movements are ultimately traceable to forces acting within this fixed arena. If space is relational, as Leibniz argued, then its very existence is contingent upon the objects and their interactions. This suggests a more dynamic, emergent reality, where the universe creates its own spatial framework as it unfolds. It implies that space is not a backdrop, but a living consequence of existence. And if space is an a priori intuition, as Kant proposed, then our perception of reality is fundamentally shaped by the very structure of our minds. We don't just perceive space, we actively construct it as a framework for our experience. This profound insight bridges the gap between the external world and our internal consciousness, suggesting that our human way of knowing is inextricably linked to the nature of space itself. In the modern era, with Einstein's general relativity, we've moved beyond even these profound philosophical debates to a scientific understanding where space is not merely a container, but an active participant in the universe's grand drama. It is curved by mass, and it dictates the paths of objects, including light. This means the very geometry of the universe is not fixed, but dynamic, changing, breathing with the celestial bodies within it. Light rays, which we might imagine traveling in perfectly straight lines, actually follow the curves of spacetime. Imagine a distant star whose light reaches your eye after bending around the immense gravity of a galaxy. This bending is not due to the light changing direction in some empty void, but rather because the space itself has curved, and the light is simply following the shortest path through that curved space. As you lie here, enveloped in quiet, let these concepts wash over you. The vastness of space outside, the subtle complexities of its nature, and the incredible journey of human thought to comprehend it. From the simple 3 dimensions we grasp intuitively, to the interwoven tapestry of 4-dimensional spacetime, to the philosophical debates that question its very existence, space remains a profound mystery, a source of endless wonder. Let your mind expand with the idea of its boundlessness, its infinite potential. Feel the quiet stability of the earth beneath you, a body moving through curved spacetime, yet feeling so still and calm. The thoughts of ancient philosophers, the calculations of modern scientists, all merge into this singular pursuit, understanding where, and how, we exist. Allow yourself to drift into the contemplation of nothingness and everythingness, the idea of a universe filled to the brim, or one where space is only defined by what fills it. There is a deep peace in realizing the limits of our current understanding, and the boundless potential for future discovery. Let the whispers of philosophers and the equations of physicists become a lullaby, guiding you deeper into relaxation. The universe is vast, intricate, and beautiful, and we are privileged to ponder its mysteries, even as we prepare for rest. Tonight, as you close your eyes, perhaps you can imagine not just a dark room, but a gentle curve of space around you, a soft hum of a continuous field. Let the thoughts of dimensions, of relations, of the mind's framework, soothe you. You are part of this grand, cosmic continuum, a tiny yet significant point in the infinite expanse of spacetime. Rest well, dear friend. May your dreams be as vast and as peaceful as the space we have contemplated tonight. Sleep deeply, and may you awaken refreshed, ready to explore the wonders of another day within this magnificent universe. Good night.